We are going to continue on with our manipulation of the canonical partition function. So the partition function is a general term for basically the summation of all the configurations in the system. Now the canonical partition function adopts this particular form. Where the energy of the system is going to be a function of the number of particles, the volume of the system, and the temperature. We'll also refer to this as beta. It's a little bit easier to do the math using the reciprocal of temperature than it actually is the real temperature. So then the challenge is going to be, how do we construct the energy of the system as a function of the number of particles in it and the volume of the system? Now this is going to depend on how we're modeling it. Now the temperature is introduced here, but you also could imagine having temperature being involved in there depending on the model that you're particularly using. So what we discussed next was that the canonical partition function could be written as the partition function for an individual particle raised to the number of particles in the system. So you would have basically partition function of particle 1 times by partition function of particle 2 times by partition function of particle 3. And then we divide it by, in the case of indistinguishable particles, an indistinguishability factor, which is the n factorial, which is the number of particles times by the number of particles minus 1, so on and so forth. This is for indistinguishable particles. For distinguishable particles, we didn't talk about this, but we can basically apply the same logic. Let's say we have particles of type J. We can have the partition function of J raised to the number of particles of J, like so. So it's the same concept. And when we start manipulating the partition function with respect to calculations of entropy, let's say entropy of mixing, we have to consider the fact that you have indistinguishable versus distinguishable particles. If I mix two boxes of indistinguishable particles, I should get no entropy change of mixing. If I mix two boxes filled with distinguishable particles, then I should get an entropy of mixing. But effectively all we're doing is multiplying the probabilities. Right? We multiply the probabilities of all the different partition functions, and in the case that they're all indistinguishable, it doesn't matter if we swap two of them around. Those are the same number of configurations of the state. With distinguishable particles, it does matter. Right? So this is exactly the same concept of this, except we're just multiplying it by particles of type I, particles of type J, particles of type K. What we also talked about is that we could break down the individual partition function for a single particle. Where the partition function for A and the partition function for B would be some sort of independent energy mode. So the example that we talked about was, for example, that QA could be the partition function with respect to translational energy, X, Y, Z kinetic energy motion. Partition function for B could be, let's say, for example, vibrational modes or rotational modes, and so on and so forth. Now this is just a tool that we can use to simplify our math. Remember, all of this came into being in the late 1800s, early 1900s. So simplifying the math is a really important aspect associated with it. Let's see, does that catch us up? Okay. That catches us up sort of as a general overview. So what we're going to do now is apply these principles here. And I guess the last one that we talked about was that the internal energy is the average energy of the system, which is related to the, let's see if I didn't make a mistake, I'm trying to pull that one off the top of my head, is related directly to the energy of the system. Yes, I got that right. So the partition function is a little bit of an abstract concept, but we're basically going to be treating it like a state variable of the system. So what we're going to do today is we're going to calculate the energy of a particle in a box. Then we're going to manipulate this expression here using classical thermodynamics and basically calculate what is the pressure, what is the Helmholtz energy, what is the entropy of the system. So it's not going to be the most rigorous derivation in stat mech history, so we're going to rely very, very heavily on what we learned in classical, which I think is fine. I don't think any of us want to participate in the rigorous derivation of the stat mech. Okay, so particle in a box. What we're going to be assuming here is that we're going to have a collection of non-interacting particles. So effectively, this is going to be an ideal gas. So more or less, we're going to solve for the behavior of one particle in a box and then assume that all the particles behave exactly the same and don't interact with one another. The second assumption is this is going to be a monatomic gas. It means the energy associated with the particle in the box is only going to be the kinetic energy. No rotations and no vibrations. So the energy for a particle in a box, we're just going to grab this from quantum mechanics. Right, remember it corresponded to 3 different kind of quantized parameters. So for simplicity, this big coefficient here, I don't want to write it every time, I'm just going to call that A. Now in terms of a term you may have been familiar with, this sort of factor in front here is also related to something called the de Broglie wavelength of a particle.
What is an M there?
M is the mass of the particle.
Okay.
V is the volume of the system. H is Planck's constant, and these are integer parameters, 1, 2, 3, 4, 5, 6. So that means that this is our energy function here, which means that we can write the single particle partition function summing up all of the states we can also write this one here as in summing up all Lx, summing up all Ly, summing up all Lz, right? Because these are the only parameters that we're changing, right? If we're holding the volume of the system constant, the number of particles in the system constant, the only difference between the states are going to be what the parameters Lx, Ly, and Lz are here. Now we can then further break this apart using a similar approach that we use to derive this property here, right, which is the independent energy modes. If Lx, Ly, and Lz are all independent from one another, then we can actually write them all separately. So we can have the summation over Lx multiplied by the summation over Ly multiplied by the summation over Lz. And then this relates to Q in the x direction, the partition function in the y direction, and the partition function in the z direction. So these are going to be independent energy modes. How we know they're independent is because based on this mathematical function, we can do this. Since we can break apart them all, it doesn't matter. The particle doesn't care what its velocity is in the x direction, determining what's its velocity in the y direction. So, effectively, this is the sort of the stat mech portion of what we're doing. The rest of it is just math. So the question is, can we evaluate this integral here? If we can, then we can calculate the partition function, we can take its partial derivative, and then we have the internal energy of the system. But we can make it a little bit easier for ourselves. So what we'll do is we want to replace the summation with an integral. I, for one, do not enjoy working with summations, particularly summations that go on for infinity. It's non-trivial, and I think we learned that when we worked through the homework problem looking at calculating the partial fugacity of a virial function. It's not trivial. You can't generalize it. You have to kind of sum it up and then figure out what it's going to go to. So the key question is, what is the difference between a summation and an integral?
One is discrete, the other one is continuous.
Exactly. So the key thing is we can approximate a summation with an integral if the step sizes are really, really small, right? We can approximate a discrete summation as an infinite summation using the integral. So what we'll do here is we're going to look at this coefficient A. So in the energy of a particle in a box, this can be equal to 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, right? But if this coefficient A is really, really, really small, then it doesn't actually matter that these are integers because the step sizes are really, really tiny. So what we'll do is we'll look at it. So, as it turns out, if we plug in all the variables, A is on the order of 10 to the minus 33 ergs, in which case 1 erg is 10 to the minus 7 joules.
And is that for like, what kind of volume is that corresponding?
Oh, sorry, good point. This is for one atom, which is approximately 10 to the minus 22 grams and a volume of 1 liter.
Okay, so macroscopic volumes.
Yeah.
Okay.
One particle in a macroscopic box. At room temperature and pressure, then beta is equal to 10 to the 16 ergs. So that means that beta times by our coefficient A, which includes the Planck's constant, the volume, the mass, all that jazz, this is going to be approximately equal to, on the order of, where do I have it here? 10 to the minus 17. I vote that's a very small number, right? So even if we're starting off here in this summation, right, we could have 0, 0, 0, for example, or 1, 0, 0. But in that case, that results in a function that's only 10 to the minus 17. So these are really small, really closely spaced points. So we're going to be okay replacing the summation with an integral, which makes our life a whole lot easier. So what we're going to do then is we're going to evaluate Q, the partition function of the single particle in the x direction, noting then that we can just take that to the power 3 and it accounts for the y and the z, makes our math a little bit easier. Okay, so Qx is the summation over all of the numbers in x, e to the minus beta times by our coefficient a, Lx squared. We're going to replace this, in this case here, Lx is 0, 1, 2, 3, 4, 5, 6, 7. We're going to replace this with an integral going from 0 to infinity. Right, there is no bound in what the velocity of the particle could be. I guess we're ignoring relativity here. And I'm just going to write this actually as e to the minus a prime. Now this function does not actually have, I believe, an analytical integral, but it actually has something called the error function is the solution. So in this case here, we have, I will call minus a prime is equal to minus beta times our coefficient a, which is equal to minus beta times Planck's constant and the 2/3, just for the sake of completeness for the notes and for the video. such that our partition function for a single particle in the x direction of the velocity, this will be equal to ERF is the error function. So this is one of these functions that comes up a lot in mathematics, and so it's sort of entabulated. So if you type in ERF or ERFC into MATLAB, it'll know exactly what's going on. But it comes up so often that it's just useful to have it tabulated somewhere. So you could look this up in an old math book, for example. You'd have tables of the error function that have been pre-calculated. So what it looks like, the error function looks something like this. Whereas your, let's say, your independent variable goes to infinity, the error function goes to 1, the independent variable is 0, gives an error function of 0, and likewise in the reverse direction, goes to negative infinity goes to 0. So that means our partition function will reduce down to using the limits of our integration, integrating from 0 to infinity. Error function at infinity is just simply 1. Error function of 0 is 0. And then we can get a function for the partition function here. Let me write this bigger in order to be small. Let's see. The single particle partition function is not just the x direction, it's the x and the z and the y. Okay, it's just the single thing that we've done already, just raised to the power of 3, because we've integrated out the parameter L out of all these expressions. So it doesn't matter whether or not we started with integrating with respect to Lx. Oops, sorry, this should have been dLx. Let me mathematically precise. And so we get a value for our single particle partition function. All right. It doesn't seem like much, and it's not much yet. But now we have a way to directly calculate the internal energy of a single particle in a box. Right, the partition function itself is a little bit of an abstract concept, sort of like entropy or Helmholtz, it's just a number, but it allows us to do a lot of really important calculations. So let's calculate the internal energy. Now what we've done is the simplest of all of these calculations, because as I just erased it, we're assuming that all the particles are non-interacting, that the energy modes are all independent. Now for a dense fluid, that may not be the case. For a dense fluid, let's say for example, the rotational energy modes are not going to be independent from the density. So if you're trying to calculate your partition function, you would have to consider what's the density of the fluid and how that density of the fluid is impacting the, let's say for example, the rotational modes. So it gets a lot more complicated. So our partition function for a collection of particles, in this case we're going to say indistinguishable non-interacting particles, is going to be the single particle partition function multiplied, or sorry, raised to the power of the number of particles. And then we have an indistinguishability factor, noting that it doesn't matter which particles in which energy state, it's the same configuration of the system. Now this partition function, what it conceptually represents is a summation of all of the states of the system, meaning that according to the ergodic hypothesis, the partition function contains all of the information necessary to calculate a time average thermodynamic property. So in this case here, the partition function for a collection of particles So all I've done is taken this function here, raised it to the power n, and divided by the indistinguishability factor, the n factorial. So let's calculate the internal energy. The internal energy is equal to the negative of the natural log of the partition function, partial derivative with respect to beta, holding the number of particles and the volume constant. Again, these are just kind of courtesy reminders, because when we take the partial derivative, all of the variables are constant. Okay, let's take the natural log of this function here. So it's going to be negative natural log of n factorial. In this case here, we have, let's see, plus 3 over 2n natural log of 2m pi over h squared minus, beta plus n ln of v. We're going to go one more step further. First of all, this is not a function of beta, so that goes to 0. This is not a function of beta, that goes to 0. With log properties, we actually have to break this one down a little bit more so. This is not a function of beta, so that should all go away as well. Which gives us the result of the internal energy is going to be partial derivative of natural log, which is going to be what? 1 over beta. So we get 3 halves n over beta, which is equal to 3 halves n kBT. Hopefully that looks a little bit familiar. Now let's say, for example, the number of particles is equal to Avogadro's number, in which case the internal energy would be 3 halves RT, which is exactly what we should expect from classical thermodynamics. This is the internal energy of an ideal monatomic gas. Let's go one step further. The heat capacity is the partial derivative with respect to temperature, in which case this is going to be 3 halves R. Now this is exactly the situation that you're going to get when you consider sort of the old way of thinking in class, in sort of undergrad thermodynamics, where they say, oh, you get 1/2, right, of a heat capacity per degree of freedom. Now as we expand on this, I think this week, we'll expand this to include rotational and vibrational modes, and we'll see that this value will change a little bit. So out of the sort of dark abstract of the partition function, it works out quite nicely to a sort of an intuitive conclusion that we're all familiar with. Okay. Now, we have calculated the internal energy. Let's continue onwards and calculate some additional thermodynamic properties. I'm going to be a little bit hand-wavy with the math because it's really just calculus manipulations. The Sandler book does an excellent job of walking us through these calculations. So if you'd like to see the details, please go through there. The book is excellent in the fact that it actually goes through and doesn't say that really obnoxious thing like, it's obvious or it's saved for an example. It actually goes through and helps you out for a lot of these ones. All right. So what we're going to ultimately be doing is we're going to be relying on classical thermodynamics. The objective of the math that I'm going to skip over is the combined first and second law of thermodynamics. Right? This was the reigning king of thermodynamics at the time of Stat Mech. Right? This has never been disproven. This relationship right here basically says that if you follow this relationship, the first law and the second law are not being violated. And the first and second law have never been violated. So this is a pretty good ground to stand on. So what we're going to try and do is we want to manipulate this equation that we've derived for the average energy of the system in the canonical ensemble. We relate it to the internal energy. So what we're going to do is basically expand the partition function, expand Q with respect to, in this case, let's see, T and V. In this case here, we'll write U as, this is the form that we've been working with in terms of beta. But if we substitute in this case here, we multiply it by, we can do minus K, no, it's plus KBT, sorry. Plus KBT squared. Right, we can work in units of temperature instead. So then the goal, I'm not going to do the math. I don't think it's particularly instructive. But basically, we're going to take this expression here, insert the terms into this expression, and manipulate it to get it to look like that. That's going to be the goal of what we're trying to do. But in many ways, it'll look very similar to how we developed and how we manipulated this expression to get us something in terms of dH and dG and ds and dA, right? Particularly in terms of temperature and pressure, right? Hopefully everyone remembers those from, I don't know, maybe a month and a half ago. So let's say we go through a lot of math. What we're ultimately going to get is that we can get this big, messy, complicated expression. Let me write this a little bit different. skipped over all the math, but assuming that sort of we trust the formulation here, this is exactly the same format as this one here, meaning that we've got T, this big term right here is going to be ds. This is going to be pressure, and we have dV. So we have plus Ts minus P dV. So this one we don't have to manipulate very much. For ds, the rate of change of entropy, we need to integrate it. The good thing about this is that when we integrate this expression, what is the entropy at temperature equals 0? 0. That's the third law of thermodynamics. So because of the third law, at T equals 0, entropy is equal to 0. That means we can derive an expression where the entropy is just equal to pressure is equal to and this would be a constant N and V, this would be a constant N and T. Lastly, the Helmholtz energy is U minus Ts. So if we take all of our expressions that we've developed so far, the Helmholtz energy is by far and away the nicest and most compact one. All right, let me just add in internal energy here. Oh yeah, minus d. And we have basically a pretty complete collection of macroscopic thermodynamic variables from the canonical partition function. Now, just as how we can calculate, for example, the internal energy as a function of any thermodynamic variable, we can calculate the Gibbs free energy as a function of any thermodynamic variable. But different thermodynamic functions are easier to manipulate in certain ensembles. The canonical partition function, NVT, is exactly the same as the native variables or the most convenient variables for the Helmholtz energy. And it gives us that sort of an intuitive conclusion, that the partition function in the canonical ensemble is directly related to the Helmholtz free energy. We can still calculate the other thermodynamic functions, but it's a little bit more cumbersome. One thing we'll also note is that from classical thermo, if we go back to our important sheet, right, with all the key variables, the partial derivative of the Helmholtz energy with respect to volume is directly related to the pressure. Again, we can see that here. Partial derivative of the partition function with respect to volume is again related to the pressure. And likewise, the partial derivative of the Helmholtz with respect to temperature is directly related to the entropy. And in this case here, this is just the result of the product rule. Sorry, chain. I always get the chain rule and the product rule confused. The one where you do the first times second and second times first, that one there. Product rule. So, now we've got all the tools available that we can actually calculate macroscopic thermodynamic properties for the particle in the box system. Do we have any questions up until this point here?
So never mind, I'm good.
Why is S and ds the same equation?
Why are S and ds the same equation? It is because integrating, so this, what is it called? The first postulate of calculus? What is that one called? Fundamental theorem of calculus, right? So the function is equal to the integral of the differential. So then, in this case here, the reason why we don't have a constant of integration is because of the third law of thermodynamics stating that the entropy is 0 at temperatures equal to 0.
So 0 is the constant of integration, basically.
Bingo, yes. One last one here, the chemical potential. Is going to be equal to this is exactly the same as in classical thermodynamics. The chemical potential is the partial molar Helmholtz in a constant temperature volume system. Now, we're most commonly working with the chemical potential in the constant temperature, constant pressure, in which case that would have been the Gibbs, partial molar Gibbs. Right, so all we're doing is we're applying the classical definition of the partial molar property and substituting in the canonical partition function. So we're effectively just treating the canonical partition function as a state variable, which it is. Right? It doesn't matter how we got to a particular temperature, pressure, or volume consideration. The canonical partition function is always going to be the canonical partition function. This is why I like the Sandler stat mech book, is because we go through the principles of stat mech, but as soon as we can latch back onto classical thermo, we do, which I think it makes things a little bit easier. And then for manipulation here, we can calculate enthalpy, heat capacities, all those different things. But it's just sort of a unpleasant mathematics. Okay, let's do pressure. Let's calculate that. What outcome should we be expecting? For a collection of non-interacting particles, how should we expect the pressure to vary as a function of temperature, volume, and number of particles for a non-interacting system? What should we expect? So what do we call a function that relates pressure, temperature, volume? Equation of state. So which equation of state should we expect for a collection of non-interacting particles? We should get the ideal gas law. So we should be getting P equals nRT over V, or we should be getting nKBT over V. In this case here, N is in moles. In this case here, N is in physical number of particles. That's the relationship between the statistical world and the classical macroscopic world. But all the relationships are the same. So at any time you're working through an equation in StatMech and you see KBT, just imagine, oh, that's kind of like R. When you scale it up to a number of molecules corresponding to continuous count. Oh, I just erased the partition function, which was silly. I shouldn't have done that. So from our equations that we've derived, the pressure as a function of the partition function is the Boltzmann constant multiplied by the partial derivative of the partition function with respect to changes in volume, holding everything else constant. Our partition function, for a collection of non-interacting particles. Let's see if I can, where is this here? Where am I? Oh, here it is. Okay. I think this is a little bit different. Last time I had, I used beta in the nomenclature. In this case, I've substituted in temperature, but that's the only substitution it was from earlier in the notes. All right, let's calculate the pressure. All right, let's do a little bit of approximation here. So when I take the logarithm, everything that's not a function when I take the partial, anything that's not a function of v will go away. When I take the logarithm, I can break this apart into additive contributions. Let's do this ln of here. So I'm going to lump everything that's not as a function of volume together. So that includes the 1 over n factorial, the 2 pi m kbt over h squared plus n ln of v, right? So everything here is not a function of volume. So this all goes to 0, which means that our pressure is going to be equal to the constant n, and the natural log of that is going to be, I think I'm missing something. I'm missing a t somewhere. I screw up. Oh, this is where I messed up. I did not see that t there. We have the ideal gas law for a particle in a box. So a couple of different other ways that this will be written. Right, the density is the number of particles divided by the volume. So if we substitute the density in here, oftentimes you'll see the ideal gas law from a statistical or physics perspective written as rho kBt, or actually as rho over theta. These are all equivalent forms of the ideal gas law. And you'll oftentimes see these two forms in more physics-oriented texts. Which I think is interesting. All right. The last little bit, we're just going to hammer out if we had applied this particular partition function for the particle in a box to the other thermodynamic variables. The internal energy, just to have it in one place, we've already demonstrated this already, is 3 halves n kBt. The heat capacity is the partial derivative of the internal energy with respect to temperature. So this just gives us 3 halves nkb. Remember, if this is Avogadro's number times the Boltzmann constant, this just goes to R. So when you're doing stat mech calculations, even though you're given an explicit equation, you would be surprised how frustrating it is to make sure it actually gives you a coherent value. Because you always run into the situation where you're like, should I times by Avogadro's number? Should I divide by Avogadro's number? So when you're running through these calculations, you'll find yourself very frequently in a situation where you'll hit enter in your calculator and you'll get something ridiculous, like times 10 to the minus 70, or times 10 to the minus 50 or 60. And usually what it means is that you made a mistake by, let's say, multiplying by Avogadro's number when you should have been dividing by, or vice versa. But that 10 to the 23, if you mess it up, that gives you a 10 to the minus 46 error, or 10 to the 46 error, depending on if you unintentionally multiplied by Avogadro's or unintentionally divided. Right? You're doubling the problem. So that's one thing to keep track of in StatMech. When you hit enter and your number is extremely small, that's probably because you're considering the energy per particle, not necessarily per mole of particles in the system. All right, so the Helmholtz energy is just the So in this case here, for Helmholtz, we're not taking the partial derivative with respect to any other independent variable, which means that there's going to be a whole lot of lingering features here because none of this goes away. It's all going to be there, and the free energy contains all of the information of the system. Whereas the pressure, internal energy, they're only looking at how it changes with respect to other variables. So the problem though, how do I evaluate 10 to the 23 factorial? I challenge any one of you to enter that into your calculator and see if it gives you a real number, right? So what we have to use is an approximation. So I will substitute in this expression here. So we can, instead of putting in the single particle partition function, I don't want to write out the whole thing. Right, so in essence, this is really just an evaluation of the Helmholtz function, but instead of substituting this expression in here, we're just going to have it left as the single particle partition function. I think I need a pen here. So this right here is going to be the challenge. So in stat mech, we use something called Stirling's approximation. So how this works is that we approximate the natural log of the factorial of a large number as n times the natural log of n minus n, which is also equal to n natural log. And as it turns out, for any number larger than, I don't know, it gets better and better as the number gets large. Where that transitions is somewhere on the order of, I think, on the tens of numbers, maybe the hundreds. I don't recall. It's been a while since I looked into that. But this approximation is critical for being able to calculate real properties. Otherwise, there's no way we could calculate n factorial to such a large number. So with this approximation, we can write that the Helmholtz energy so effectively what we're doing here, this n times natural log of q e over n, that's just this expression right here. Right, so that's where we get the e and the n, and then we minus it out and all that kind of stuff. So if we substitute it in all of its glory, and we have an expression for the Helmholtz energy of that fluid. And just to run it out, so we have all of them in one spot. Let me just write this here. Running out of space. Okay. We have calculated a statistical mechanics result for all of our most commonly encountered thermodynamic classical functions, but starting from the particle in a box perspective and manipulating them in the canonical ensemble, which is constant temperature, constant volume, and constant number of particles. So now, there's additional complications. So we assumed, and I don't think I have it written anywhere here, that the energy of the system is only a function essentially of the kinetic energy, and that none of our particles are interacting. So there's multiple ways we can make this more complicated. Number one is we can make it so it's not only just the kinetic energy. We can include electronic state transitions, meaning electrons jumping to higher and lower orbitals. We can include rotations, the molecule physically rotating around, and we can include vibrations. If we include all of those energy modes, we will have a more accurate prediction of the heat capacity of the fluid, and we can also include temperature dependencies. As it turns out, the kinetic energy is directly related to the temperature, so there really is no temperature dependencies because that is the temperature. But with respect to more complicated and real molecules, higher temperatures means the system has more kinetic energy, which means that it might activate different modes of energy storage. So as we increase the temperature and we increase the number of states in the system, which is what the partition function represents, our heat capacity should increase, our internal energy should increase. So this is going to be a way for us to allow and interpret macroscopic properties on what they mean on the molecular length scales. Then the really, really complicating one that is going to be challenging is right now we're assuming that these are all non-interacting particles, and that the non-interacting particles, all of their energy states, are independent of the states of all the other neighboring particles. That's going to be the one that is going to break us down when we start looking at dense fluid properties. So stat mech is all fun and games when we're dealing with basically particle in a box with an ideal gas law. But as soon as we start considering multi-body and interparticle effects, then the partition function now becomes not a function of Lx, Ly, and Lz for every independent particle, but it becomes a function of what all the particle positions are with respect to all the other particle positions. So when we integrate the partition function, right, we don't integrate it with respect to all these little variables. We integrate it with respect to holding the positions of all the particles constant except for particle 1, and moving that one to every single space in the system. Then repeating that process, but holding all the particles' positions constant except for particle 2, and integrating all the positions there. As it turns out, that's not feasible to do so in a direct analytical way. So it starts down to coming into approximations. How do we approximate dense fluid structure? And this is where a really important concept, the radial distribution function, comes in. So this is the starting point. Once you start, non-interacting systems are actually pretty straightforward. But once we start introducing interacting systems, it becomes exponentially more challenging. And so we're only going to really kind of kiss the surface with respect to those challenges. Any questions? I will see you all at the help session, or those who need the help, tomorrow in the afternoon, let's say 2 o'clock.